In this video, we'll take a look at how pH changes throughout the course of a titration. First, we'll look at strong-strong titrations, where a strong acid is titrated with a strong base, or where a strong base is titrated with a strong acid. First up, a strong acid titrated with a strong base, such as 50 milliliters of a 0.2 molar nitric acid solution titrated with a 0.1 molar sodium hydroxide solution. Throughout the course of a titration, if the pH is monitored, it can be analyzed as a function of the amount of titrant added. And that's what you see there in the graph. This is called a titration curve or a pH curve. We've got pH on the y-axis, and for this particular titration, the volume of the base that is added in milliliters on the x-axis. You can see at the beginning of the titration, before any base is added, we have a very acidic pH because we only have a strong acid to start with. As we add base to our acid, we see an increase in pH as the acid is neutralized. Eventually, we reach what's called the equivalence point, and if you remember, that is the point in the titration at which the amount of titrant added is just enough to completely neutralize the analyte solution. So in this case, we've added enough base to exactly neutralize the acid. That's called the equivalence point. And you can see that the pH there is 7. So anytime we add a strong base to a strong acid for titration, the equivalence point is going to occur at a pH of 7. Prior to the equivalence point, of course, we have the acid to start with, and we should see a pH that is less than 7. Now let's look at the type of salt that is formed in the reaction between a strong acid and a strong base. You might remember when we do acid-base reactions, we're doing double replacement. So swap out the cations or swap out the anions, and we get water and a salt. Okay, so it's the salt that we are focusing on here. In this particular example, it is NaNO3. This is a neutral salt. Neutral salts have no effect on the hydrogen ion concentration or the pH when dissolved in water, and therefore give a neutral solution. They are formed from the cations of strong bases and the anions of strong acids. And so our strong acid was nitric acid. Its anion is the nitrate ion, and then the cation of the strong base, sodium hydroxide, was sodium. So whenever this happens, we get a neutral salt, and it has no effect on the pH of the solution. Next up is a strong base titrated with a strong acid. For example, 100 milliliters of 0.5 molar sodium hydroxide solution titrated with 1 molar hydrochloric acid. Once again, on our titration curve, we see pH versus, this time it is the volume of hydrochloric acid that's added. So that's what we are adding to our base as we are doing our titration. We start with a pH that is quite high because we have only base at the beginning of the titration. And then as acid is added, the pH decreases, and eventually we reach the equivalence point. You can see the equivalence point once again is at 7. So prior to the equivalence point, we have a pH that is greater than 7. And then at the equivalence point, once again, we have a pH of 7. And this is because we once again get a neutral salt that is formed in the reaction between sodium hydroxide and hydrochloric acid. So both of these salts that are formed are neutral. Finally, for both of these graphs, notice there is a pretty long vertical section of the graph right around the equivalence point. You see it there on the strong acid titrated with a strong base. And then the second graph, you see like right here, where the strong base is titrated with the strong acid. They have this in common. Next up, we've got strong-weak titrations. So a weak acid titrated with a strong base or a weak base titrated with a strong acid. So let's look at 50 milliliters of a 0.1 molar acetic acid solution titrated with a 0.1 molar sodium hydroxide solution. Once again, we have our titration curve. Notice that it is missing that vertical portion of the graph right around the equivalence point that the strong combinations had. Notice the pH starts out acidic as we are starting with acetic acid. And then we are looking at what happens to pH as a strong base is added. So initially our pH is less than 7, and if we wanted to know what it was exactly, we could do an ice chart. But then something happens about halfway to the equivalence point. It's called the half equivalence point. You can see that our curve kind of flattens out for a little bit. So maybe about from here to here. This is referred to as the buffer region because the pH remains constant. We only get this buffer region with strong-weak titrations. And we can actually calculate what the pH is at this half equivalence point. Because it's a buffer region, we are talking Henderson-Hasselbalch. But because we are halfway to the equivalence point, that means that half of our acid has reacted, so we're at half the concentration. And then conjugate base now has been produced in the same amount. So this ratio right here is 1, and the log of 1 is 0. So at the half equivalence point, pH equals pKa. Notice on the graph that the equivalence point occurs at 50 milliliters of base added to our acetic acid, and the half equivalence point occurs at 25 milliliters. This is where we have neutralized half of our acid. At the equivalence point, you can see that we have a pH of 9. So in general, we will see a pH that is greater than 7. This happens whenever a weak acid is titrated with a strong base, and that is because the salt that is created is basic. We've got our base and our acid. We do our double replacement. We get water and our salt. And in this particular example, sodium acetate is what we call a basic salt. This is where the anion of the salt, so in this case, the acetate ion, it is the conjugate base of a weak acid. So therefore, it can go back and reform that weak acid when it reacts with water, which would be in the solution. And you know it's basic because it is making hydroxide ion. So for basic salts, look at the anion, and if it comes from a weak acid, it can go back and reform that weak acid, along with, of course, hydroxide, making it a basic salt. And just to refresh your memory, here is the net ionic equation for this reaction, where we get rid of the spectator ion of sodium. Remember, weak acids don't dissociate or ionize well in water, so we keep that together. HC2H3O2. Next, let's look at a weak base titrated with a strong acid, such as 100 milliliters of 0.05 molar ammonia titrated with 0.1 molar hydrochloric acid. Here's our titration curve. Notice the pH starts high because we're starting with our base, and then we are adding acid to it. Our equivalence point occurs once we have added 50 milliliters of our hydrochloric acid. And so then the half equivalence point should be at about 25 milliliters, where that little dot is. And right around there, we should have kind of a flat area called, again, the buffer region. So maybe something like that. We see that the equivalence point occurs at a pH that is less than 7. And that has to do, again, with the type of salt that is produced. But first, we have a pH that is greater than 7. You could, again, know exactly what that is if you did an ice chart. And at the half equivalence point, pH equals pKa. At the equivalence point, we see a pH that is less than 7. And as I mentioned, that has to do with the type of salt that is created. When ammonia reacts with hydrochloric acid, we get ammonium chloride, and this is an acidic salt. Acidic salts are when we have an acidic solution that's formed from the cation of the salt, and it is the conjugate acid of a weak base. So we had ammonium chloride as our salt, and ammonium is the conjugate acid of the weak base ammonia. So that means it can react with water, go back and reform the ammonia, and we get hydronium ion, which makes the solution acidic. So for acidic salts, we are looking at the cation, and for basic salts, we're looking at the anion. As we look at the net ionic equation for this reaction, after we get rid of the spectator ion of chloride, we can really see that relationship between the ammonia and the ammonium. So now let's work on calculating that exact pH at the equivalence point with weak, strong titrations. This was the first example that we looked at where a weak acid was titrated with a strong base. That made the salt sodium acetate, and then the acetate ion can react with water, go back and reform acetic acid along with hydroxide, making a basic solution. So we will be looking for a basic pH when we're done. So exactly how much acetate do we have to start with? We start with 50 milliliters of 0.1 molar acetic acid. So that is 0.005 moles of acetic acid. We would need that exact same amount of moles of base of sodium hydroxide to neutralize the 0.005 moles. And because the entire reaction is 1-to-1 ratios, we would get the same number of moles of sodium acetate. So 0.005 moles of acetic acid, 0.005 moles of sodium hydroxide required to neutralize that, and then 0.005 moles of acetate ion from the sodium acetate that is produced. But that acetate is in now a new volume of solution since we're adding a base to neutralize all of our acid. If you take a look at the titration curve, you see that the equivalence point occurred at 50 milliliters. So 50 milliliters of base were added to 50 milliliters of acid to neutralize. That should make sense because they are equal concentration, and that makes the total volume 0.1 liters. So the concentration of the sodium acetate, or specifically the acetate ion, is 0.05 molar. That's what I'm going to put in my ice chart. For my products, my acetic acid should be 0 at the equivalence point. We've added enough base to neutralize all of the acid. And same for the hydroxide, that should be 0 as well. We are, of course, ignoring the hydroxide that's just due to the water. All right, an ice chart. You know what to do, right? Minus X, plus X, plus X. Okay, and now, because this is the conjugate base of the acetic acid, to solve for X, we need a Kb. Now remember, we talked about if you have a Ka and you need a Kb, we can take 1 times 10 to the negative 14th and divide it by that Ka value of 1.8 times 10 to the negative 5th. That gives you a Kb of 5.6 times 10 to the negative 10th. Now you're ready to solve for X. X squared in the numerator, and then in the denominator, we're going to see if we can do without the minus X. So we'll do 0.05 and solve for X. X is 5.3 times 10 to the negative 6th molar. That is the concentration of the hydroxide ion, which will give us POH. Negative log of 5.3 times 10 to the negative 6th gives a POH of 5.28 and then a pH of 8.72, which makes sense because we said when we have a weak acid that is titrated with a strong base, we get a basic salt and we should see a basic solution. So the trickiest part of this is, what is this initial concentration of the ion that comes from the salt? So the moles of acid and base should be the same. That's the definition of an equivalence point, where you've added enough base to exactly neutralize all of your acid. And then again, because everything's in a 1-to-1 ratio, the moles of salt is also that same number of moles. And then we need to divide it by the total volume that would be in our flask once the titration is complete. So now what about our weak base titrated with a strong acid? Let's once again find that exact pH at the equivalence point. This time we looked at 100 milliliters of 0.05 molar ammonia titrated with 0.1 molar hydrochloric acid. So if you look at the graph at the titration curve, you will see that the equivalence point occurred at 50 milliliters. We needed only 50 milliliters of hydrochloric acid because the concentration was double of the concentration of the ammonia. That will be important, of course, when we go to figure out our total volume. But first, let's find our number of moles. So 0.05 molar, 100 milliliters, which is 0.1 liters, gives us, once again, 0.005 moles. And we're going to take that number of moles and divide it by the total volume to get the concentration of ammonium that's in our ammonium chloride salt. So that is 100 milliliters and 50 milliliters, so that is 150 milliliters total. 0.005 moles divided by 0.150 liters is 0.033 molar. That is the concentration of our ammonium ion initially. Initial concentrations of the ammonia and the hydronium should be 0. And now we can do our minus X, plus X, plus X, and solve for X. So we need a Ka for this because ammonium is forming an acidic solution. It's an acidic salt. Also in the equation, you can see it's a proton donor. So we need a Ka. And again, 1 times 10 to the negative 14th, the Kw divided by the Kb will get us the Ka of 5.6 times 10 to the negative 10th. Substitute the Ka into your equilibrium expression. We get x squared over 0.033. We're going to try to do this without the minus x, and x equals 4.3 times 10 to the negative 6, which is your hydronium ion concentration, which you can use to calculate the pH. The negative log of 4.3 times 10 to the negative 6 gives us a pH of 5.36, which is less than 7. It is acidic. It does make sense because this salt that's produced in the reaction between a weak base and a strong acid is going to give us an acidic salt. And finally, just a few other things about titration curves. We were looking at some characteristics of the graphs. The first one looks at a strong acid versus a weak acid when it is titrated with a strong base like sodium hydroxide. So we looked kind of at the vertical part of the strong acid, strong base graph. You definitely do see that there. You're not going to see that as much with a weak acid. In the diagram next to it, this is a polyprotic acid. So this would probably be 2 protons that are donated, or it would be a diprotic acid. And this is what the titration curve would look like. You would have a equivalence point maybe right about here. And that would make your first half equivalence point maybe somewhere in here. So that would be for the first proton. And then for the second proton, equivalence point would maybe be right about here. And the half equivalence point would be maybe somewhere in here. And finally, you can see that when you have a weak acid titrated with a strong base, the Ka value, or the strength of that acid, will definitely affect how that curve looks. So you can see stronger acids with a Ka of 10 to the negative second down here toward the bottom. And then we've got some lower Ka values up here toward the top, like 10 to the negative 10th. And you can see kind of how that affects the pH, of course, at the beginning. And then what pHs we're seeing the half equivalence point and the equivalence point occurring at. So hopefully this gives you a good idea of what titration curves look like for strong titrations and strong, weak titrations, along with some ideas about what kind of salts are created, what kind of pHs we see at the beginning, at the half equivalence point, if applicable, and at the equivalence point.